Okay, welcome to the lecture number 40. So, we have been discussing about the spin stabilization. So, you may be wondering why we are discussing about the spin stabilization. So, later on you will see once we start with the reaction wheels and the control moment gyros. So, at that time you will see that though the reaction wheel it is used to actuate the satellite, but if suppose I have a satellite, let us start because we need the this concept. So, we will discuss it here. Say this is a satellite and inside this I have a wheel mounted on one axis. So, it is rotating about this axis. So, if this wheel is rotating on this axis, so what you are doing that you are giving it momentum bias, angular momentum bias. So, from outside the satellite may not be rotating. Okay. It is possible that from outside the satellite is not rotating and you have already set the wheel rotating before putting it into the orbit. So, whatever the direction of the initial direction of the satellite, it will be maintained until unless some disturbance comes into picture. So, the same thing we will look through one gyros through the YouTube video, and if you want you can go and look yourself in those videos. So, there you will find that once a spinning wheel, okay, it is a put in a box. So, there is a box in which it will be inserted, okay, and then it is left on this corner. So, this box remains in this position itself. So, you can understand that the satellite behaves in the same way. So, you can consider the box to be the satellite and there is a wheel rotating inside, okay, which you are not able to see what is inside there, but because of this wheel this box will be able to maintain this position. So, the same thing whatever we have been discussing about the spin stabilization. So, here this refers to the case where the your spinning velocity may be constant. So, the any other changes are not taking place, but there can be case like this wheel is spinning here and if I further increase the angular speed, means we accelerate we give it angular acceleration to this wheel. So, you will see that because this system is free from the external torque, this is my satellite which is free from the external torque. So, the total angular momentum must be conserved. Here if we are torquing it, means there is a motor here, suppose in this place there is a motor and this motor is once you pass electricity through this motor. So, this wheel will accelerate. Okay, you can increase the voltage input. So, that the wheel goes at a faster speed. So, once it accelerates, so you can see from outside we are not applying on this any other torque. Okay. So, the angular momentum of this system, this plus this must be conserved as a whole. So, this implies that if it accelerates here in this direction, means the anti-clockwise. So, this will the satellite, the outer part of the satellite, it will go in a opposite way, means it will go this way. So, it will start rotating here in this way. So, this way by actuating a motor inside, by putting input signal to the motor, and we can make the wheel accelerate and thereby we can make the satellite rotate about this axis. So, we can similarly if we have on other axis, say if I have a bigger box and I have 3 wheels mounted here, one wheel here, one wheel along this axis and another wheel on this axis. Means they are perpendicular to each other on 3 different axes. Okay. So, by moving these 3 wheels you will be able to control the angular orientation, angular velocity of the spacecraft. So, in that context we are using this as a torquer inside. Okay. So, it acts as a torquer, but if it is moving at a constant speed, if its speed is maintained, then it will try to point in a particular direction, and this is what we are studying here in this particular topic. So, spin stabilization, it refers to the case where the satellite is set into the motion along one of the axis, and then thereafter the satellite keeps rotating along that axis. So, it may be that because of the internal friction, your the wheel may start dying out. So, you would like to maintain at the same angular velocity. So, that can be done, obviously that is a different issue, it is a circuit issue, basically electrical engineering or either electronics issue, whatever it can be said. But the main thing is here the dynamics part, that if your there is a angular momentum bias inside. So, if I have a angular momentum vector here. So, until unless I apply an external force on this or external torque, it is not going to change its orientation. So, the same thing you can consider through, say we have a rotating wheel and somebody is handling it here, okay, a person is holding it and he is sitting on a chair which is a revolving one. So, he is sitting on a chair and it is a revolving one, then let us say that it is a rotating like this, okay, seen from his side. So, so it is something like this. This is or we take this. So, suppose this is the axis. So, around this axis it is rotating like this. Okay. So, it will rotate like this. So, there is a wheel, or you can think of like a you can think of like a cycle wheel. This is a, suppose this is a cycle wheel and here this is your axle, okay, and this wheel is rotating. Okay, so, it is rotating in the anti-clock based direction. So, if the we look from the this person sitting on this revolving chair point of view. So, we will change the direction, it will look something like this. Okay. If we look from the person side, from this side, so it will be revolving in this direction, and if this person he applies a torque on this axle and tries to change its position from this position to this position. Okay. So, this wheel comes from this position to this position. Okay. So, here in this case you can see that this is the angular momentum vector. Here the wheel speed is remaining same. So, this angular momentum vector goes here in this place. So, there is a net change here in this direction, okay. Little bit inclined, because this if we show this as the magnitude. So, it will appear like this. So, it is a little bit inclined, okay. It goes like this. So, and this is your delta H. Okay. So, we know that this delta H by delta T, this is nothing but our torque. Okay. So, this implies that the change of this vector from this place to this place, it implies that there is a torque applied along this direction. So, as a result of this, now I am not going to discuss the whole details, but as a result of this, this person will rotate on this axis. Okay. So, here a torque is so, So, he starts, this person starts rotating about this one. Okay. So, why he is rotating? Because what he is doing, that he is applying a torque to this wheel, okay. And as a reaction of this, because this is free to rotate. So, this one is rotating. So, in which direction it will rotate and other things, we will discuss it in the once we start the
सर टच को ऑफ कर दिए, टच ऑन है शायद सर वेबसाइट में.
Okay, so we will discuss these details later on. So, we go to what we have been discussing earlier. So, whatever we are discussing, it is purely relevant to the satellite, because you are not going to actuate the satellite continuously in the orbit. So, what is required, that if the satellite is going here in this orbit, so it should be pointing in a particular direction inertially, or it may be that it is always pointing toward the earth. Okay. So, a camera is there which is always pointing toward the earth. So, in that case it is required that it rotates at a constant angular velocity about this axis, okay. Or it may be required that all the time the satellite is pointing in a particular direction, okay, which is in the case of the Hubble telescope. You know that it is used for measuring the location of the stars. So, this is inertial orientation, and while this is the earth pointing satellite. So, both these jobs can be done through the spin stabilization. So, say here in this case, if I have a wheel which rotates such that its angular momentum vector is directed along this direction. So, it will try to maintain its orientation, and we want to study here whether this kind of configuration, like here my Hubble telescope in the orbit, okay, and there is a aperture here through which the star at a distance it is being observed. So, whether it will maintain this orientation throughout the orbit or not. So, this is what we are trying to study. So, we have written the Euler's dynamical equation, and then we are trying to get into the get through the dynamics, that whether this kind of rotational configuration, where this suppose this is rotating here, or in the case of the Hubble telescope, we cannot afford to rotate the whole telescope itself, but here inside we can put some wheel which is rotating, and then it is trying to maintain this orientation. This is possible, or either some very precise active control system, just like the reaction wheels, or like your the small thrusters are there, which are micro thrusters available. So, this can be used to continuously maintain a very precise direction. Okay. So, that becomes a part of control once you are using the thruster continuously and trying to maintain the orientation. But if we are trying to put a momentum bias, just like we were discussing here, that this wheel is rotating here, and therefore, this will always point here in this direction until unless it is disturbed. So, that kind of configuration we can achieve. So, that is called the stabilization part, but here it is a because it is a coming because of momentum bias. It is not because of the external torque being applied. Okay. If or the internal torque itself, so that we are we have the reaction wheels inside, which is being rotated, and it is trying to maintain this orientation. So, that is part of the controls, that you point it in a particular direction, but here we are not discussing at this stage any matter about the controls. We are discussing about just about this dynamic system, where one wheel is rotating inside, or itself this is a satellite which is rotating on its axis. So, whether it is stable or not, whether it will maintain this orientation or not, this is the topic we have been working with. So, in this context, we worked with the Euler's dynamical equation, and there we saw that we derived this equation theta 1 double dot plus 1 minus k C theta 2 times and another equation that we derived this equal to 0 and theta 2 double dot we got this equal to 0, means theta 2 dot this will be a constant and therefore, theta this will, let us say this constant is c. So, this will evolve with time. So, C t plus, let us say this, and we can write it in this format. Okay. So, this says that here the theta will continuously grow with time. We will discuss about this issue. Let us first develop this. So, in this context, then we wrote alpha 1 equal to theta 1 cos theta 2 plus theta 3 times sin theta 2. So, basically this part we are taking from this place theta 3 sin theta 2, s theta 2 is nothing but your sin theta 2 and similarly cos this is cos theta 2 and theta 1 times cos theta 2, this part is written here in this place. And alpha 3 then we wrote as minus theta 1 sin theta 2 plus theta 3 cos theta 2. Okay. So, we utilize this information to get theta 1 double dot, this particular one, okay, in terms of alpha, okay, and the rate of change of alpha. So, we have derived using this. So, follow from your last lecture. Here c theta is nothing but cos theta 2. This theta we have replaced by, unnecessarily we are not carrying this 2 notation. We understand that this is the pitch angle we are using here. Okay. Similarly, s theta is sin theta 2. Okay. So, this we have derived in the last class. So, the way we have derived, similarly we can derive theta 3 dot. Okay. So, for this we need to work out using this. So, theta 3 dot we can write as alpha 1 dot s theta So, what we have done that the alpha 1 we have written this equation alpha 1 and alpha 3. So, we differentiated this, okay. And after differentiating this we are trying to get this theta 1 dot and theta 2 dot, but so I will write the previous step, so that there is a continuity. Multiplying equation of alpha 1, which is our equation number 3, it is equation 3 by sin theta 2, and this we are writing as sin theta, means we have written this as s theta, okay, in the short notation. So, multiplying equation by 3 by sin theta 2 and equation 4 by c theta, means this is cos theta 2, and adding okay, that yielded us the theta 3 equal to alpha 1 sin theta 2 plus alpha 3 cos theta 2. Okay. Similarly, equation 3 by c theta and equation 4 by minus s theta, and adding else theta 1 equal to okay. Thereafter, what we have done that we were interested in, see here the equation we have, this is bit involved equation. So, what we are interested in that we want to replace this theta 1 double dot and theta 3 double dot, and here theta 3 dot, theta 1 dot, okay. All these quantities theta 1 and theta 3 here. So, in terms of alpha 1 and alpha 3. Why we are doing? Because we see here in this place, okay, these are not constant terms, okay. These are the periodic terms. It's this coefficient, it's a time dependent term, which is a periodic term basically, and solving in this format, it's a formidable. So, it's a better to reduce it in the format where the coefficients they all appear in the time independent format. So, this manipulation, so this assumption we are doing to get rid of this periodic coefficients. So, for this we are assuming this that the alpha we are defining one variable alpha 1, another variable alpha 3, which is equal to theta 1 cos, this part basically this part has been copied here in this place, okay. And alpha 3 another variable has been defined like this, just by changing this to with minus sign, okay. And these two equations then we are using to get theta 3 and theta 1, and thereafter we are differentiating these two equations. So, by differentiating, and we have got this equation last time, okay, theta 1 double dot, and similarly theta 1 dot also we got. So, I will just make a note of that this here in this place. Okay, so, the theta 1 dot we have got as alpha 1 dot c theta okay, though we it's written afterwards. So, this equation is differentiated to get this equation, and that we have already done by arranging the terms and all other things. So, I need not repeat all these things, but for the continuation of the lecture I have to reproduce all these things here. This is the difficulty we face, because there are equations and we move once the lecture ends for a particular day. So, we have to recall all the things so that we can proceed. Okay, so, first we got this, from there we are getting this theta 1 dot, and from there then by differentiating this and doing all the replacement or the insertions, we are getting this theta 1 double dot. In the same way, by differentiating this theta 3 equation, we get this equation. So, if you differentiate it, you will get this equation. Okay. And where we have used this theta dot, we have written as omega s plus omega 0, and so theta dot is nothing but your theta 2, and so theta 2 dot, this is nothing but your omega r, because this is the Euler angle, and this is being measured with respect to the orbital axis, with respect to the orbital axis. Okay, and this we have I have explained you in the last lecture. So, theta 3 dot we have written, if we differentiate that, so we get theta 3 double dot. You can check all these equations, because it is a time taking. So, I am doing it quickly. So, we are using this equation is being differentiated. This is equation number 8. Okay. Now, we have got this theta 3 dot also, and we have got also theta 3 double dot and theta 3 dot. So, we need to insert these values here, like theta 3 dot is here, okay, and theta 1 dot is here, theta 3 dot is here. So, theta 1 double dot. So, all these quantities we have derived earlier. Okay. So, these quantities need to be inserted here in this place, and we need to rearrange this equation. So, rearrange these two equations. So, if we rearrange these two equations, so we get it in a simpler format where the coefficients are independent of time, okay, means they turn out to be the constant coefficients, and therefore, those equations can be solved easily. The stability of the system can be described in a easy manner. So, now insert all these things. So, we take the first equation here, we have theta 1 double dot, we take this equation, the first equation. Okay. So, inserting for theta 1 double dot, theta 3 dot and theta 1 and all these parameters here. In equation 1. So, equation 1 I am reproducing here. So, this part is your theta 3 plus sin theta 2 theta 1 times cos theta 2. So, this we are writing as alpha 1. So, alpha and this c theta 2 we are writing as c theta, okay, this part. So, here c theta we have written and then we are writing here alpha 1. So, this equal to 0. So, this looks little shorter than the previous equation. So, from different equations we need to insert all these values. So, theta 1 double dot, this quantity then becomes alpha 1 double dot c theta this equation is bit long. All these things are tedious, not difficult, but tedious. This is this particular term, it is written here in this place. This equal to 0. So, this has got converted here into this format. So, still we need to rearrange it because the you can see that S theta, C theta, all these terms are there. So, still it is these are the periodic terms. So, we need to eliminate. So, we need to rearrange this equation. Rewriting the above equation. We are rearranging the above equation. Omega r being replaced by omega s plus omega 0. So, these terms we need to rearrange it. So, by rearranging we can see that this gets reduced to so expand it and check this term. So, I am writing the final result here in this place. These are the few shortcuts I have taken. Okay, so, we can insert these values here. So, this gets then simplified. This is our equation number 10. Similarly, the equation for theta 3 dot, it can be reduced. So, still you can see that these are sine and cosine dependent terms. Okay. So, still we have not got rid of these terms. So, this is the equation for theta 3 dot that we have written earlier. See, here we have taken the case of the satellite which is symmetric about one of the axis. It is called the inertial symmetry. So, so because of that your equation is getting simplified. Otherwise, if you look for the 3 axis satellite, okay, because in that case your theta 2 double dot, this has got reduced to 0. If you do not assume that symmetry, so this will not be equal to 0. So, that will pose another problem. Okay. So, the equation it becomes formidable. So, in this place wherever the k is appearing, this k we have assumed it to be I 0 minus I divided by I, where I 0 is the moment of inertia about the I 0, this is about the axis of symmetry. Okay, so, theta 1 double dot we have already reduced. Now, we are working with theta 3 double dot. So, inserting for already we have got theta 3 double dot, theta 1 dot, theta 3 etcetera. So, insert all these things here. We cannot avoid this mathematics. Alpha 3, this is c theta. So, we are inserting these values here. You can develop the whole thing, you do it yourself and then match it. It requires little patience, but you can do it. So, this equation has been written here. Okay. Now, we need to reduce it. So, these terms can be rearranged. Now, we need to replace this omega r by omega 0 plus omega s. if you are genuinely interested in learning this subject, then you must derive all these things, because at one stage or other stage I have derived all these equations. Okay, so, this one we have reduced and written here in this place. So, do this part yourself. Okay, so, multiplying equation 10, the previous equation, this equation, and equation 11, this particular one, okay, by c theta and s theta and adding. So, you can see that there are the terms. So, if we multiply like the equation 11, this equation by s theta, so we get here s square theta term, this will be s square theta term, and here alpha 3 times c theta times s theta. If we go on the previous page, so the previous equation we are multiplying by this c theta. So, here this we are multiplying by c theta. So, alpha 1 double dot c square theta, and here in this place we are getting alpha 1 double dot sin square theta. So, this term will add up and we get alpha 1 double dot, and we get rid of this sin theta term here. Similarly, this term is here alpha 3 double dot, this comes with a minus sign, alpha 3 double dot, and this comes with a plus sign. So, this term will get eliminated while you add. So, thereby we will get terms which are independent of periodic or time dependent coefficients. Okay. These are all the terms we need to add. So, some of the terms will drop out, this term drops out. Okay. Then we have the term here, this term and this term drops out, and here this term and this term drops out. So, this equal to 0. So, this gets simplified to alpha 1 double dot plus 2 omega 0 1 plus k. Here this term and this term will add up, this gives us alpha 3 dot, this is with minus sign. Okay. Similarly, here this term and this term adds to give minus alpha 1, okay, and these two terms add together alpha 1, this equal to 0. So, you can see that in this equation we have got rid of all the sin theta and cosine theta terms. So, therefore, here let us first write this equation, rewrite it. So, minus 2 omega 0 alpha 3 dot omega 0 alpha 1 plus 3 omega 0 square k times alpha 1, this equal to 0. These terms and this term, because alpha 1 is common. So, we combine it, so this is the equation in alpha 1. Okay. Similarly, we will, but here you can see that alpha 3 dot it is appearing. So, still it is a coupled, okay, means the roll and the yaw they are remaining coupled, they have not got dissociated. So, equation 10 we have multiplied by, this is equation 10 and this is equation 11 by c theta and s theta. Now, what we are doing, that we are doing it by s theta and c theta. Okay. So, there we have added, here we have to subtract. And subtracting equation 10 after multiplication from equation 11 after multiplication. So, basically we have equation 10 here. So, this equation 10 we have to multiply and equation 11 we have to multiply. So, we have to subtract this equation. So, we will put a minus sign before this. So, this is our equation number 11 and this is our equation number, this particular equation. Okay. So, we are going to multiply this particular equation, which is equation number 10. So, for equation number 10, once we multiply, so alpha double 1 dot s theta, we are subtracting. So, I am putting a sign right now here. And then we need to simplify this. So, whichever the terms they drop out, we need to eliminate them. So, we can see that this term they cancel each other. Okay. Then what else we have here? These two terms will add up, this term and this term they will add up. Okay. So, this way we have to look for the terms which can cancel out and which will add up. So, here we have this term here alpha 3 dot multiplied by this quantity, okay. And the same quantity appears here with a minus sign here. Okay. So, this term and this term will drop out, okay. They will cancel each other. Similarly, we have a term here which is multiplied by this alpha 1 s theta c theta, and we look for this term here, this is the term. So, here you see that before this there is a minus sign. So, this term and this term will drop out, this term will drop out, and therefore, this equation can be simplified. Okay. So, if we add and simplify these equations, simplify them. So, this gets reduced into this format alpha 3 double dot s theta square plus c theta square Okay. So, we have got these two differential equations, and these differential equations can be solved now, because you see here this term it is a completely constant, this term it is a completely constant, omega 0 is a constant, spin rate you are taking this as a constant, okay. And omega 0 is the orbital angular frequency or the orbital frequency. So, the coefficient now in this equation they turn out to be constant. Here also all the coefficient this and all these terms are constant, and therefore, the simplification is possible. So, this has already got simplified. Now, we need to work with these equations and look into the dynamics of the system, how the system will behave. Whether it is a we are interested in looking for stability of the system. So, through these two equations we are going to look into the stability now. So, we will continue here in the next lecture. Thank you very much.